pleased to welcome you here at RSC event dedicated to the announcement of our new solution for the high-performance computing. My name is Alexey Moskovsky. I'm a co-founder and CEO at RSC Group. Our company develops technology for ultra-compact and energy-efficient solutions for the HPC. And at the beginning, that's my pleasure to invite the first speaker, senior analyst from Intersect 360 Research, Michael Feldman. Please, Michael, floor is yours.
There we go. So yeah, I'm Michael Feldman with Intersect 360 Research. I'm actually the newest member of Intersect 360 Research. And we're a small group, there's 4 of us. We're in Silicon Valley, and we specialize almost exclusively in high-performance computing, supercomputing, doing market analysis and research. Today I'm going to talk about some of the trends that we see that are driving what's going to be announced today, what RSC is announcing. Market trends in energy efficiency, density, scalability, software investment. So I'm going to sort of talk about this in the context of exascale. And I think we've sort of seen these challenges before. And if you'll notice, I mean, we've actually seen these challenges way before exascale. We talked about power and energy efficiency, compute density, memory bandwidth, memory wall problem, application scalability, system software issues, and reliability redundancy. I mean, these are things that are called out exascale, but more broadly, these are the things that are challenges in performance computing for decades, you know, at least 1 decade, at least 2, now more specifically to exascale, because this is extreme scale. But these have been driving quite a bit of time by now. And even though exascale is maybe 7 to 8 years away, we're already seeing some systems that are starting to conform to some of these challenges. And it's not just RSC doing it; the whole industry is enveloped in this. I'm not going to talk about all those things I just went through, but one of the things I'm going to narrow in on a little bit is power.
Excuse me, could you speak up just a little bit?
Sure. Is that better?
Yes, thanks.
So power, I mean, we've done some research in this area. We have a group of people we survey, and you'll notice a lot of these things about facilities are sort of flatline, they say, but power seems to be going up, and that's basically system size is going up. People want more and more performance and flops. And basically, they're building bigger systems. It's not Moore's law; can't quite keep up with what's going on. So there's this trend line, and that has a real effect. So it's 50% of the total budget of a facility in this latest survey is just power, and that's the highest I think we've surveyed since we started several years ago. And then just the other factor here, facility expenditures are about 10% of the average site budget for HPC installation. But if you look at the trend line for power consumption, that's going to be hard to maintain because if the power keeps going up at 10%, it's going to be stressed as well. But it's not like they cut back on cooling necessarily or building floor space either. I mean, those are going to be constant. A little bit about density. Density is a big thing now, not that we run out of necessarily space in the data center. It's just more cost effective to build denser and denser systems. Some of the foundational technology of this are the co-processors, which I think are driving a lot of the increase in density and performance now. Accelerators, co-processors, whatever you want to call them. Right now, most of them are discrete, but there's some integrated co-processors out there now that are being paired up with CPUs in certain cases, well, of various kinds of CPUs from a few companies. And just straight up CPUs, x86 and ARM and Power are, I think, the 3 sort of industry standard CPUs we're going to see over the near term going into exascale. We don't know what that mix is right now is obviously too early to tell. We haven't surveyed any ARM sites. Power, of course, is IBM, but they've opened it up, so we might see a little bit differentiation there. But they're all industry standard or open standard architectures, and there's probably not much room for custom architectures as we go forward for the majority of this market, as it's been for quite some time. And the other part of density, especially now we're starting to see people talking about on-chip fabrics, on-chip adapters. That's going to be a big thing. Every microprocessor company is going to be involved in this to one extent or another. It's going to also have the density. And then the memory, I think we're going to start to see 3D memory and maybe some of these more exotic technologies that I've listed there. Those are a little further down the line. 3D memory, I think, is more near term than any of these. And certainly by the time exascale comes into being, I think 3D memory might be much more standard. Some of one or more of these others might be in the mix as well. And then just in general, over and above the components is we're seeing denser server design that are sort of enabled by what's going on there. So more sort of innovative designs where we pack more into a server box than we've seen before with shared infrastructure with power supplies, things like that. Getting back to the coprocessors and accelerators, we have done some research on this, and we are seeing a definite ramping up of the accelerators. It was sort of flat as it began with GPUs, and last year, nearly half of the new systems being bought today are now with accelerators in our survey. And so we're predicting certainly by next year, majority of new systems will be accelerators. And certainly with Intel's entrance into the market, I think that's conservative. I think there's going to be a preponderance of systems in 2014 that come with, maybe not fully stacked accelerators, but with a lot of them. And even now, about a quarter of all deployed systems out there from previous years have accelerators. So we've definitely seen the ramp up. It's certainly beyond the experimental stage. And this is certainly technology that's going to go forward, and a lot of people have seen that's where a lot of the performance for exascale is going to come from in one form or another, not necessarily what the forms we're seeing today, but more integrated or socket compatible or socket integrated components. So I'm just going to talk a little bit about software investment, because that's a big deal. It sort of is a conservative break for all the new hardware innovation. Certainly we've seen that around the coprocessors and accelerators, that the software investment is harder to carry forward because there's new programming models that you need for accelerators, which tend to be many core architectures. So right now, software represents about 14% of the total HPC budget, which is significant. It's not as much as the hardware, obviously, which is about half of it, and software tools account for about a quarter of that. But the important thing here is users have invested years and in certain application areas, sometimes decades, in these software development efforts for single applications. So they want a pathway to get there. If they're going to exascale, they don't want to rewrite necessarily any of these things from scratch, not if there's thousands of lines of code, tens of thousands of lines, but they don't want to do that. They want to see a software path, not necessarily with the same component architecture, but with the same set of software tools in a lot of cases. And I think that's what we're seeing sort of with many core environments now. Some of these software tools that are emerging right now are going to be a central part of that path into many core at the exascale level. And some of these, right now we have a lot of competing models, or not a lot, we have a number of competing models for these. And I think we're going to see that shake out a little bit over the next few years. But even the ones we have now, they're all open to a certain extent. They've become industry standard to one extent or another. And even though they're competing APIs, they're all getting very good adoption. I don't have this chart here, but even though half of the systems we think, or nearly half the systems are accelerated systems, close to 80 or 90% of people are already looking to put accelerators into their systems, and they're going to have to pick one of these software models. And for legacy applications, these applications that have been around for decades in this community, they're going to be drawn to the path of least resistance. I don't know where I am on time, but I'm going to keep going because somebody pulls me out. Actually, this is my last slide, so I'm good. So the long view. We talk about exascale, of course, but the first exascale machine is likely to be a custom machine. But most of them won't be. Most of them will be industry standard machines with mostly industry standard components based on hardware and software that you can buy with machines of much lesser status. And by the time the middle of the next decade rolls around, there's probably going to be dozens of exascale systems. But more importantly, that means there's going to be thousands of petascale systems. Basically, petascale in a rack, actually several petaflops in a rack, probably, at a price that thousands of people will be able to afford. And there'll be millions of terascale systems, because you'll put that in one desktop machine. So it's not just exascale. We're going to build a few dozen exascale systems that are going to be interesting. This is going to have petascale for everybody. And then just this last comment, the technology will be further refined that we see now as we approach the exascale era. The things that we're going to hear about today and that we'll be hearing about for the next several years as we gear up for exascale at the end of the decade and early next decade.
Thank you, Michael. Questions? Okay, maybe we will have a questions and answers section later. Thank you for identifying challenges. And to answer challenges, we need to provide solutions. And to build solutions, we need partners. First of all, our partners is Intel. And I invite Vice President of Intel Architecture and General Manager of Technical Solution Group, Hazra, please.
Thank you, Alexander. Nice to see you. It's a pleasure to be here, see some old friends, and some new friends, hopefully. This is exciting. As Michael was walking through kind of the context, both the technological and economic context for paying exquisite attention to energy consumption, I hope it dawned on everybody that this is a fundamental area of both challenge, and along with challenge comes opportunity. So innovative solutions that provide new kinds of densities, that enable new levels of performance, that unleash the ability of system vendors to create these solutions for various kinds of missions and workloads is what we do at Intel. And in this case, I'm very, very pleased to be partnering with the RSC group to break the stupendous achievement that you'll see today announced in a few minutes. It took a lot of partnering and work. These kinds of densities, it's co-designed at a different level, at the server board level, including ingredients that go into the system, how they're laid out, and in some cases, even the silicon has to be modified in order to reach stable systems with this tremendous amount of density and new cooling technologies. We're very pleased to see RSC put this innovation to use and innovate on top of what we've been able to do to enable a new class of solutions that maybe the world hasn't quite seen ever before. So congratulations. It's been a tremendous partnership. We hope it will continue, and it will be a huge success in the market.
Thank you for warm words. I invite Stephan Gillich, Director, EMEA Technical Computing. Please.
Hello, everyone. It's a pleasure for me to stand here, right? Also because, as you note, I'm the director for HPC in EMEA, right? And this new thing, which we'll see in a minute, actually comes from EMEA. So this is a great honor that I've been asked to give a little bit of an overview of our technologies which help in exascale computing and in this petascale in a rack system we will see very soon. So if you look back 2 years, around about 2 years, some of you might remember that Kirk Skrogan at that time made an announcement that we are really serious about exascale, right? And we could have shown this slide at the time, and actually I think we had one version of this slide back then, right? And this is actually a picture of what we think is required as fundamental building blocks for building exascale type systems or on the road to exascale. So obviously you need the performance, right? That's very obvious, right? If you want to reach an exascale of performance, you need processors who can actually deliver that performance. Do we have that today? Well, if we take enough of them, we would have it. But with that comes a challenge, power efficiency, right? So if we would just take what we have today, yes, we could build a system, but it would take, well, several power plants to really power it, right? So that cannot be, so we need to do something about power efficiency. On the other hand, if you really throw so many processes together, you might run into problems with really maintaining the resiliency of a system which is actually required to run certain serious things on the system, not just a benchmark, and even just for the benchmark, it might be a challenge, right? So that's another thing we are working on, and you have to also interconnect all of those pieces in a way that you exchange the data fast enough with enough bandwidth and low latency so you can run real applications on the system as well. Last but not least, obviously, the last hardware element you need is enough memory to put your data in. And then, last but not least, if that wouldn't be challenge enough, you need to program that animal as well. So a real bunch of problems we need to work on. And what we have said 2 years back and what we have followed on, and I'll show that in a minute, what we are concretely doing, is really take up this challenge and work on it, right? And we're gonna see one step forward today, actually, with this product announcement. So let me show just quickly on how we address the needs of this, right? So obviously there are the hardware building blocks which we provide, and this is pretty well known. I think when you think about Intel, you probably have that in mind. I guess so. So we have the processors, the Xeon processor as the main workhorse of HPC. Actually, the top 500 list was just announced. So we have 412 systems, I've been told now, of that list, which is 82%. So that clearly shows we're kind of successful in that, and that's just the top 500. And there's lots of things below that, which I think are equally important. We tend to show only the top things, but I think the real development behind that is enabled by the high technology for high performance is also the millions of users who are actually now able to simulate serious things for product development and other things, right? So that's important. To be able to cope with applications which are highly parallel in nature and to really make effort on enabling petascale level and going into exascale level of performance, we have introduced actually this year the Xeon Phi coprocessor. We have announced the architecture also a couple of years back in Europe. Some of you might remember the mic architecture, and this is the product we follow up with it right now. And recently, we also have engaged ourselves more into the fabric space to really be able to integrate all of these things together. And what's not on the slide, what is also important, that Intel is a small silicon provider as well. So we can really take technology and put it onto silicon in high volume and also do steps of integrating more and more building blocks onto the silicon. We have made a step to integrate major elements of the interconnect, the I/O side and things like that, right? And we are capable of integrating more technology on our silicon as well. So after the silicon, there comes the software, and this might be less known that Intel is very much engaged in the software space as well, with our tools here, which play an important role because you see two types of processors here, processor and coprocessor. They share common elements of an architecture, which we call Intel architecture. And on this architecture, we have the same tool set, which is really important going forward if you want to be able to program those machines which have this high performance. You need to have programming models and tools to really be able to do that, and do that consistently across the architectures you have in your system. And so we are engaged in our own products, but also very much in standard setups, because we are a big believer in open standards, Intel is, and that will enable the industry in the direction of petascale and exascale computing as well. And then obviously we integrate hardware and software into systems. We have various products here as well, which are going to the board level and really integrating some of this technology we have been speaking about before. And last but not least, we're also working with the end users, because we very much believe in that we need to make this technology usable for the end user. So we have big dialogue. Yesterday we had our roundtable with, I don't know, 400 people, I think, just end users out of some of which we see here today as well, just to have a dialogue on, okay, here's our technology. What is it really what you need from us in the future to solve your problems, which is very important to us. And I want to highlight one thing which we actually announced in Europe as well, just about 2 weeks back, or actually 3 weeks, I think, on October the 22nd, and I'm personally involved in this a lot as well, is the Intel Parallel Computing Centers, where we are actually working together with end users to work on community codes and really make an effort on parallelizing them in a way that they are really future-proof when we integrate more and more parallel structures into the future with petascale and exascale computing. We also have exascale labs in place, by the way, which we've been talking about and working in since several years. So what I wanted to say, we're really serious about this path from petascale, multi-petascale. We have a system with 33, so 3% of the exascale, 3.3% today. There's a long way forward, but we are on the way with that, and we have the right technologies and good products on our roadmap going forward. And now, I think, with all the words, we will see some of the reality today. Thanks a lot.
Thank you, Stephan. So we come to the central part. I invite my partner to do the hard job, introduce the product. Alexey Shmelev, Chief Operations Officer, RSC Group, please.
So I'm today supposed to speak about RSC PetaStream, the product that we are launching today. And if I were asked to define the product in one sentence, I would say that this is 1 petaflops per rack. This is industry record. I don't know any example of industry product which would contain that amount of computational performance in 1 rack. And we really consider this to be a practical path to create exascale level supercomputers. First of all, I would like to speak about future HPC opportunities. Of course, the list here is not a complete list. And I mentioned that this list is absolutely in line with Intel understanding of exascale path. First of all, we would consider many coprocessors as one of the most promising approaches to increase the computational power. But this approach imposes some questions to applications, to the software paradigm. You can see them here. Also, a very important question, a very important opportunity, is growing number of nodes in a system. This places questions to scalability, to mean time to failure, and also to density, as real geometrical size of the system is limited. The footstep is limited. Very important question is power delivery and cooling, as as you know, supercomputers now consume more and more power, and this is a very complicated engineering question, how to deliver that power and how to cool these systems. So someone would call these items as challenges, but we would prefer to call them opportunities, because this is an opportunity to succeed. This is an opportunity to offer better products. And I would like to convince you today that our vision of the answer to all those opportunities we provide in our new solution, RSC PetaStream. So this is our new prototyping and our new developing result in this solution. So introducing the new RSC PetaStream ultra-high density HPC solution. What were our motivations and what are the values of this solution? So first of all, from our point of view, this is a massively parallel system to address exascale needs. As I showed in a foil before, the needs, we think that this is the system to address those needs. So it provides many core processors. This is the right system for programming them, for trying to develop new software. Also, a very important thing from our point of view is that this system protects investment into software development. Thanks to Michael, we are familiar with general problems in software developments on the path to exascale. And this system provides ability to protect your investments, as this is standard x86 architecture. And as you can reuse existing applications, and you can protect investments in optimization of many core platforms, for software for many core platforms. Also, this is a very flexible platform for customers. There are no two identical customers, of course you know about that. Everyone has its own business needs, and this platform is really very flexible to address all those needs. So we can provide a variety of interconnects and topologies, and a lot of other options with storages and interconnection design. As you know, RSC is one of world leaders in providing energy-efficient solutions. So our marketing differentiator is providing of solutions with direct liquid cooling. And I think that I can say that we know how to do that. Since this new product utilizes RSC's technologies on direct liquid cooling, I think this is a really very energy efficient solution. Also, it is equipped with system management and monitoring, which also affects and contributes to energy efficiency. So just again, we use as a basement of our system compute chip, which is Intel Xeon Phi. It has 60 x86 cores. We provide compute node based on this compute chip. It has 8 gigs of RAM, and you can see all the other parameters on the foil. And after that, we assemble 8 compute nodes into one compute module. So this compute module provides power supply, it provides interconnect, it provides servicing, networking, etc. So after that, all those modules are combined into cabinets, and we have performance of 1 petaflops peak in one cabinet. One cabinet or one rack contains 128 compute nodes or 1,024 compute nodes. So it is, as I said, rack level design, so it has integrated management, etc., etc., etc. The footprint is 1 square meter. And I would like to show right now this compute module. You can see it on the right-hand side of the foil. This is the way it looks in metal. So 128 modules in the rack provide performance of 1 petaflop. Total power consumption is a bit more than 400 kilowatts per rack. It would be absolutely impossible to do that without liquid cooling, of course. We invite everyone to come to our booth at exhibition, and we'll show you the model. We'll describe all the details. So why we consider PetaStream as that it drives to exascale? From our point of view, this is a really innovative, I would say revolutionary, implementation of massive parallels architecture, and it provides world record computing density. It provides an enormous amount of threads. So it provides you with an ability to develop new software, which will be exascale software, which will be software that requires parallelism for an enormous amount of threads. And also, as I said, it provides protection of your investment. So you can use the code that was already created before this era. So, well, you can say that, of course, RSC considers this product to be the best. But in fact, when everyone speaks about some product, it is very interesting not how the manufacturer thinks about it, but what values this product provides to the end user. And the best way to find out is benchmarking. So our engineers, together with Intel, thanks again to Intel partnership, made some benchmarking. And to be unbiased, I would ask Intel senior engineer, Andrey Semin, to present the results of this benchmarking. Please, Andrey, take the floor.
I think you should hear me that. Okay, thank you, Alexey. It was actually my pleasure to work on the first prototypes of the system live and be able to run some of the benchmarks and participate in the earlier validation, including software. Well, I have just a few minutes, so I don't want to make a long technical presentation. And I decided that I will not talk about LinPack. I will not talk about any kernel benchmarks, which we actually talked a lot already. This machine is based on Intel Xeon Phi coprocessor. It actually utilizes Intel MPSS software stack, so all the things which are available and run on other machines are actually available here as well. But I wanted to show a couple of examples. Well, before I go to them, I need to show a couple of legal disclaimers. Actually, two of them. I think I have more legal disclaimers than actual things. To show you a couple of examples of applications, there's actually real applications, a lot of them from the molecular dynamics side, and I want to show you how the scalability looks. And the second is how the energy efficiency running real applications looks. Okay, let's go to the scaling example. Well, we've chosen RAMS. It's a quite widely known molecular dynamics code developed at Sandia National Laboratories, available under GPL license, and we chosen one of the standard benchmark models called Leonard-Jones melt liquid, and we run it in several configurations on one of the modules as Alexey presented today. We used latest Intel software tools and off-the-shelf Intel MPSS stack and Linux. There were a couple of modifications and optimizations made to RAMs. Actually, it's limited to about 40 source code line changes. The code itself is over, I think, several millions of source lines. It's really big code. And, well, the first one we see is scaling. Right? These are actually not just speed-ups. It's 1 million of atom time steps per second. It's a throughput metric usually derived for the LAMPS benchmarking. If you go to www.lamps.sandia.org, you will find a lot of benchmarks which compare about the same metric. And here I show for different number of computational threads. They use combination of MPI processes running several OpenMP threads each. Though this black dashed line is the ideal scaling you would get from the 240 threads to something like almost 2,000 threads. You see very close to ideal scaling. And this is what's called on LAMPS like scale size workload. So the workload increases every time well, you add more compute nodes and people's money. Okay, it's very easy to get weak scaling. What about strong scaling? Strong scaling also looks good. Strong scaling is always much harder to get because your workload reduces per compute element as you add more compute elements. And it actually still looks quite good. So the speed ups are quite interesting on the LAMPS on these workloads. And well, we of course also looked at the profiling and on single node. A lot of time, and actually some of the modifications went into optimizing compute kernel for Xeon Phi, right? And that part is called pair. But one of the interesting things that scalability derived not just by how the time of computational kernel reduces as more compute elements added, but also how the communications of this green box stays. It's actually not increasing, it's actually sometimes even reducing, which is a quite nice observation. Well, the good thing about that, there are workloads which do scale on mic architecture, they do scale on the machines like PetaStream, and either available today, run production jobs, or actually should be considered as a good applications for the future exascale. Well, one of the things, if you look here, well, it actually, in order to scale, it really have to be, some further optimizations have to be done on the lamp side. Okay, scaling is good. What about other things? So some of you know I do quite some work on the energy efficiency and power management and so on, so we actually decided to take another code as example. We did quite some additional optimization, so here we didn't touch any computational part. We did touch some computational part. It's a Gromox code developed out in Europe, in Groningen originally, and now it's actually the community development. It's used in quite a lot of places. One of the most popular molecular dynamics codes and used in like famous projects like Folding at Home or people who try to evolve artificial life, for example. It's a big source code. It's not like kernel benchmark. It's 1.6 million source line. I just checked it out from their website. I didn't count it. It's also public code, and again, we used the latest workloads. Here we took a fixed size workload. It's actually about 4 times smaller than the workload you see in the previous slide. That's water, so H2O, 1.5 million atoms, so it's 500,000 molecules of water. And the other thing, we run it, of course, on the Xeon cluster. Each node here contains 2 Xeon E5 2600, and this solid line is the runtime. It's about the same as in previous slide, showing that runtime reduces with the number of, okay, that's actually wrong. It's number of compute elements is taken from the different part. And this is a power dissipation as it grows. As you add more nodes to run fixed size workload, your average power will actually go down. And your consumed energy will be multiplication of these two. As a rough estimate to your total consumed energy in joules, or you can convert them to kilowatt hours. Now that's how it looks on Xeon Phi. It's like, looks like getting a little better. And also, again, the number, it scales also quite good. But here's how it looks if you go to compute how many joules you need to spend to run this one job on Xeon cluster or Xeon Phi cluster, such as PetaStream machine that was actually physically run on the machine and measured on the PetaStream machine prototype. Well, we see that it's like almost 2x difference over here, a little bit less than 2x difference in terms of number of joules you need to complete the same amount of work using production code. It's a large-scale application, which is, again, available today to run using this highly scalable machine like RSC PetaStream, comparing to standard off-the-shelf clusters available on the market today. That's all from my side. I don't want to bother to death with technical details. I just want to highlight that the designs like RSC PetaStream scale well, and they showcase scalability of Xeon Phi architecture as a massively parallel compute architecture. There are some specific microarchitecture optimizations needed, and we as a software engineer believe I will have a lot of jobs in the next couple of years to continue optimizing applications for many core processors. So, but there are machines which would allow to do that even today. Optimized applications deliver great performance. If you hear about applications not delivering great performance on Xeon Phi, you probably need to talk to us and we will optimize or help optimize them. And well, actually you can save energy in a factor of 2x or even more running real applications on Xeon Phi systems like RSC PetaStream. Thank you.
Great, Andrey. Thank you so much. I really appreciate your participation in our presentation. Thank you again. So I would like just to add some summary. So our computations show, our measurements show that 1 rack of new RSC PetaStream equals to 8 racks of standard RSC Xeon-based solution. So this is not the measurement of peak performance. This is the measurement on real applications, on real benchmarking. From the point of energy to solution, it will require half of the energy needed to solve the same problem on Xeon-based RSC solution. So I think that as we are one of world leaders in energy efficiency, this is a quite representative comparison. So this shows that new system is really very efficient from the point of computational efficiency and from the point of energy efficiency. So I hope this new solution will have good life. So thank you so much for your attention. We have spoken quite a lot. And I think this is, now you have some questions, and now it is time for questions and answer session. I'm ready to answer your questions. Thank you.